Hi everybody, welcome back. I think we are on notes number 4 today, and we're continuing to review different topics. And today's topic is called Basic Classes of Functions. So we're going to look at different kinds of functions that we've looked at in the past and think about the important things to know. So this might be broken up into 2 videos. We're just going to have to wait and see how long it goes. Alright, we're starting with polynomial functions. And polynomial functions are functions where, if you look at this example down here, you have a series of terms added or subtracted. You could just have one term, that's possible as well. But the thing to know is that the variable's exponent has to be a whole number. So like here you see 3, 2, 1, and you have an invisible x to the 0 on there. So only whole number exponents, not fractions, not imaginary numbers, not radicals, things like that. Linear functions are polynomials, and quadratic functions are also polynomials, but we already reviewed those a day or so ago, so we're not going to talk about those right now. Also, constants would be polynomials, like if you had f of x equals 4, that's a constant. That would also be in the same category. Okay, so we're going to look at the example h of x equals x cubed minus 3x squared minus x plus 3. That's a cubic polynomial function. And in general, what should we know about any polynomial function? Well, it would be nice to know about the domain and the range. It would be nice to know the general shape. And it would be nice to know the intercepts. So, for any polynomial function, the domain is all real numbers. You can take any real number and raise it to a whole number power, multiply it by something, add or subtract, it's still going to be real. For the range, it depends on the function. So we really don't know for sure. So let's look at some examples. And as we look at these examples, we can talk about the general shape. So if it's linear, we could have something like this. If it's cubic, we might have something like this. If it's quintic, which means degree 5, we might have something like this. If it's linear, it could be slanted down. It could be decreasing. If it's cubic, it could also be going down like that, etc. So some of these have one end up, one end down, and the range is all real numbers. Those would be the ones that have odd degrees, like something to the first power, something to the third power, something to the fifth power, etc. But if you have an even degree, like a parabola does, you would have something like that, or maybe if it's quartic, it might make a W shape, or if it's a 6th power, maybe you just have more of those things. You either have both ends up or you have both ends down. So the range is not necessarily all real numbers because it looks like there would be maybe some kind of maximum value or some kind of minimum value. So it really just depends on the polynomial. And when we're talking about intercepts, we're talking about the y-intercept as well as the x-intercepts. So some of them might have multiple x-intercepts. They all will only have one y-intercept. Now let's work on this example. Let's say I wanted to know the y-intercept. Well, the y-intercept is always the point with an x-coordinate of 0. So if I put 0 in for x, we get 0 cubed minus 3 times 0 squared minus 0 plus 3. So we just get 3. So that would be the point 0, 3. And let's say I want to know the x-intercepts. Now in general, I might say, what are the roots? Roots or zeros are almost synonymous with intercepts. Roots and zeros are synonymous with each other, but intercepts are the real roots. So let's start by finding the roots. And the way you find the roots or the zeros is you put 0 in for y. So it would be 0 equals x cubed minus 3x squared minus x plus 3. Now, when we did this unit in pre-calculus, we used synthetic division to find the factors of these polynomials. You may recall, though, there's also a method called factoring by grouping, which works a limited part of the time. It works on a limited number of problems, but this problem was made up so that grouping would work. So here's what I'm going to do. I'm going to factor x squared out of the first two terms. So we have x squared times the quantity x minus 3, and then I'm going to factor negative 1 out of the last two terms. So we have minus 1 times the quantity x minus 3. Notice that I factored the negative out, so negative times a negative is how we get positive 3. Okay, the next step in grouping is to recognize that we had a factor of x minus 3 in both parts. So we have a factor of x minus 3, and the other factor is x squared minus 1. Okay, well, x squared minus 1 is also factorable. We can factor it into x minus 1 times x plus 1. And then if we set each of those equal to 0, we're going to get our 3 roots. So we get x equals 1, x equals negative 1, and x equals 3. Those are all real, so they are all x-intercepts. So what we could do is we could make a rough sketch of this polynomial function. So let's say I have 1 here. Okay, we can plot our points. We have our y-intercept at 0, 3. We have our roots at 1, negative 1, and 3. And the end behavior, because we have a positive leading coefficient, we're going to have the end behavior like that of a line with a positive slope. So the left end is down and the right end is up. So that's a rough sketch. I didn't really get a whole lot of points, but I got some of the important points. Okay, so that's our review of polynomial functions. Now let's review rational functions. So an example of a rational function. We have a polynomial expression on the top and a polynomial expression on the bottom, and that's what makes it rational. We should know domain and range. Well, we really won't know range. It's going to depend on the function. Typically, it's all real numbers, but let's just say it depends. For the domain, you have to think about what makes the denominator 0 and exclude that number. So exclude numbers that make denominator 0. Also, you could find the intercepts. And another important thing, oops, I can't spell intercepts apparently. Another important thing about rational functions is that they are the ones that often have vertical asymptotes and horizontal asymptotes. So we want to be able to find the asymptotes. VAs for vertical, HAs for horizontal. All right, so if we look at this example, let's look at the denominator. What makes the denominator 0? That would be x equals 3. So the domain is x cannot equal 3. X can be anything else, just not 3. Now, that's where we're also going to have our vertical asymptote. Since x can't equal 3, the line x equals 3 is a vertical asymptote. So if I start a little sketch here, we would have something like this. Okay, now I'm going to just quickly go over some of the things you learned about these types of functions. To find the horizontal asymptote, we have a shortcut. Oops. Look at the degree of the numerator and the degree of the denominator. So the numerator, x to the first, so the degree is 1. The denominator, x to the first, so the degree is 1. Notice that the degrees are the same. So it's not top heavy, it's not bottom heavy. Degrees are the same. So that means that the horizontal asymptote is the ratio of leading coefficients. 1 x to the first over 1 x to the first. 1 over 1 is 1. So it's y equals 1. That's because as x goes to infinity, you would have something like infinity plus 1 over infinity minus 3, infinity over infinity. So it's like 1,000 plus 1 over 1,000 minus 3. That's very close to 1,000 over 1,000, so that's very close to 1. And then what we would do to get some points to plot is we would find intercepts. So for the x-intercept, we're going to let y equal 0. When we set the fraction equal to 0, it's only the numerator that can equal 0. The denominator can't equal 0. That makes it undefined. So if the numerator equals 0, we get x equals negative 1. So we have the point negative 1, 0. And now for the y-intercept, we put 0 in for x. So we end up with 0 plus 1 over 0 minus 3. That's negative 1/3. So the y-intercept is the point 0, negative 1/3. Okay. So based on that, we can go ahead and draw that part of the curve, and we can find an extra point over here somewhere, and chances are the other part of the curve is going to look like that. So without spending any more time on it, that's just your quick review of rational functions. Okay, radical functions we did not spend time on very much at all in pre-calculus, but just like the others, it would be nice to know the domain, and the range, and just the general shape. Okay, if you have f of x equals square root x, you know that you can't take the square root of a negative if you're looking for a real output. So with functions, we're looking for real inputs and real outputs. So you can't take the square root of a negative and get a real number. You can take the square root of 0. Square root of 0 is 0. Square root of 1 is 1, square root of 4 is 2, and if you keep going, you're going to get this kind of curve. So that's what the shape of a square root graph is. And because you can't plug a negative number in for x, the domain is going to be x is greater than or equal to 0. If you want to express that using interval notation, you can say 0 to infinity with a square bracket on the 0. Now you can find the range of that. You can just look at the y values. The range is also greater than or equal to 0, so y is greater than or equal to 0. Here's another radical function, but it's a cube root instead of a square root. And you can cube root negatives, like the cube root of negative 8, negative 2, the cube root of negative 1, negative 1. So there's no restriction on the domain. The domain is all real numbers. Let's plot a few points. The cube root of 0 is 0. The cube root of 1 is 1. The cube root of negative 1 is negative 1. The cube root of 8 is 2. The cube root of negative 8 is negative 2. So we end up with this curve that looks like this. It's the inverse of the x cubed function. Its range is all real numbers. Okay. Now here's a new category for you. It's called algebraic functions. These are produced by taking sums, products, and quotients of roots of polynomials and rational functions. So it's very difficult to know the shape of something like this because you're taking things that might be very simple that you might know the shapes of, but then you're combining them with other things and they could get really wildly different. So do we need to know the shape? No. You're just going to take it on a case-by-case basis, and this is a great time to use a graphing calculator to identify the shape of the graph. What we should be able to do, not necessarily know, but be able to do, is find the domain, graph on calculator. So for the domain of this example, think about the other problems we did. We did a problem with x in the denominator, and we said, well, the denominator cannot be 0, so in this case we would say x cannot be 1. That's the number that would make the denominator 0. But we also did a problem where we had a square root, and we said we couldn't have a negative inside the square root. So we have to have only values of x that will give us 0 or a positive inside the radical. There's no way to have 0 inside the radical because the numerator's not 0. So we're going to get a positive inside the radical if x is greater than 1. So that would be the domain. Now let me grab my graphing calculator and we can take a look at how this looks. Okay, so you grab your calculator, you go to y equals, you clear out whatever's there. You can also clear the memory of the calculator. And then we had the square root of 1 divided by the quantity x minus 1. I think that's what we had. And for a window, I'm going to try zoom standard just for a place to start. Zoom standard is zoom 6. That shows us -10 to 10 on both axes. So here's what we get. Now it does kind of remind me of a rational function, you know, the kind that had the two curves and the asymptotes, but it also does kind of remind me of a square root function because it just kind of comes to a stop right there. Okay, speaking of coming to a stop right there, I think this is a good place to end part 1 of this lesson, and then I'll just start a second video for part 2. So stay tuned.